Right now, air is moving past your skin. You don't control it, you didn't ask for it. It just arrives, brushes your arm, and disappears. Most people never wonder why. But the real answer is far stranger than a breeze. Wind is not a thing. Wind is a symptom. It's what happens when the planet tries to fix a problem it can never fully solve. Here's the problem. The sun doesn't heat the Earth evenly. The equator gets blasted with direct light almost all year. The poles get a weak, glancing dose. Even in their summer. That means one part of the planet is always hotter than another, and heat, left alone, never sits still. It moves toward cold, always, every single time. Air is just a fluid in the same way water is a fluid. Heat it up and it expands. The molecules spread apart, get lighter and rise. Cool it down and it contracts, gets heavier, and sinks. So picture the equator. The ground bakes. The air above it heats up, expands, and rises like a slow, invisible balloon. As it lifts, it leaves behind a gap, a patch of lower pressure at the surface. Nature does not tolerate a gap. Something has to rush in to fill it. That something is cooler, heavier air from somewhere else. And that rushing in is what you feel on your face. Wind isn't air being pushed. Wind is air falling into a hole that heat just carved out of the sky. Physicists and meteorologist pioneers going back to Edmund Halley in the 1600s were already mapping this. Halley wasn't just an astronomer chasing comets. He built one of the first scientific explanations for trade winds, showing that heated air near the equator rises and pulls in replacement air from cooler latitudes. He proved wind wasn't random. It was thermodynamics, wearing a costume. But here's the twist almost nobody expects. If the Earth didn't spin, wind would behave in an almost boring way. Hot air would rise at the equator, drift straight to the poles, cool, sink, and flow straight back. One tidy loop per hemisphere. Simple, predictable, almost gentle. The Earth spins, and that ruins the simplicity in the most useful way possible. As air moves north or south, the ground beneath it is also spinning, but at different speeds depending on latitude. The equator whips around at over 1,000 miles per hour. Near the poles, that same rotational speed drops to nearly nothing. So when air travels from the fast-spinning equator toward the slower-spinning poles, it's still carrying that faster sideways momentum. It doesn't travel in a straight line. It curves. This curving effect has a name, the Coriolis effect. Gaspar Gustave de Coriolis worked out the mathematics of it in the 1830s, though he was originally studying rotating machinery, not weather. Scientists later realized his equations explained something enormous. They explained why hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern one. They explained why wind never flows in a straight line from high pressure to low pressure, but instead spirals. Your instinct might say wind should blow directly from a cold zone to a hot zone, like water down a drain. It doesn't. It bends, it spirals. It gets deflected sideways by the planet's own rotation. The same way a ball thrown across a spinning merry-go-round seems to curve to someone standing on it, even though the ball is moving in a perfectly straight line to someone watching from outside. This is why the atmosphere doesn't have one giant loop of air per hemisphere. It has three. Meteorologists call them Hadley cells, Ferrel cells, and polar cells, stacked from equator to pole like invisible conveyor belts. Each one shuffles heat a little further away from where the sun dumped it, handing it off to the next cell like a bucket brigade nobody can see. That's the big picture. But wind also happens on a much smaller, faster scale, right above your head. Ever notice how a parking lot feels hotter than the grass beside it? Asphalt absorbs heat and radiates it back into the air quickly. Grass and soil hold onto that heat more slowly, so the air above the asphalt heats up faster, expands, and rises. The air above the grass stays relatively cool and dense. Cooler air slides in to replace what just left, and you get a small local breeze, born entirely from a difference in surface temperature no wider than a few hundred feet. Beaches work almost the same way, just on a bigger stage. During the day, sand heats up faster than the ocean. Air over the sand rises. Cooler air from over the water rushes in to fill the space, and you feel a steady onshore breeze pressing toward the land. At night, it reverses. The land cools faster than the water holds its heat, and the breeze flows the opposite direction out toward the sea. This is the part that tends to surprise people most. Wind isn't something added to the atmosphere. Nothing is pushing air around like a hand shoving a crowd. Wind is the atmosphere's attempt to erase a temperature difference that keeps regenerating itself every single day, because the sun keeps rising and keeps hitting the equator harder than it hits anywhere else. Climate researcher Carrie Emanuel, working out of MIT decades later, extended this same basic principle to explain something far more violent: hurricanes. He showed that these storms are essentially heat engines, machines that convert the temperature difference between warm ocean water and cool upper atmosphere directly into wind speed. The stronger the temperature gap, the more violent the resulting wind. A hurricane isn't a special kind of storm, separate from the breeze on your porch. It's the exact same physics, just turned up until it becomes dangerous. So, every gust that moves your hair, every gale that bends a tree, every hurricane that levels a coastline, they all trace back to the same single cause: uneven heating. A planet trying to smooth out a temperature gap that never actually closes because the sun refuses to stop shining harder on one spot than another. Your ancestors didn't know any of this, but they used it constantly. Sailors read wind patterns to cross oceans centuries before anyone understood why those patterns existed. Farmers built their planting seasons around prevailing winds without knowing those winds came from spinning air masses deflected by a rotating planet. They just knew the wind came from somewhere, did something, and mattered. You are not so different. You still adjust your jacket when a gust picks up. You still glance at weather apps before deciding whether to bring an umbrella. You are still, in a very real sense, reading the planet's attempt to balance its own temperature, the same way people have for thousands of years. Right now, air is moving past your skin. It arrived because, somewhere far away, the sun is hitting the ground harder than it should. That imbalance had to go somewhere. It became motion. It became wind. And it just reached you.